So in these next couple of lectures, I'll talk about coordinates, datums, and map projections. This is what we discuss in the second week, so it's readings for chapter 3 primarily. And it's the basis of all we do in GIS, these coordinates and datums. So you have to have a clear understanding of what they are. So my main points today was we have two primary types of coordinate systems, and I'll describe these in the next two lectures. The first is a spherical or geographic coordinate system, the lat-long systems that you're used to in defining locations on the surface of the globe. The second kind we use are these 2D Cartesian or projected coordinate systems. Those are the flat layer systems we use when we define data in our GIS layers. So they're in a right angle system. Now, there's a third system we use. It's called a 3D Cartesian. It's down in the technical weeds, and for the most part, we don't deal with it much in GIS. But people that get more into geodesy or really want to get into how we do the transformations among our base coordinate systems, our geographic coordinate systems, work with those 3D Cartesians. I won't talk about them much here. Now, there's this key thing called a datum, and the datum is really our roadmap to where things are on the surface of the Earth. And a datum has two parts. It has a well-defined, mathematically specified ellipsoid, which is a kind of sphere or spheroid, and it has a well-measured set of points placed on that spheroid in which we know they're spherical or latitude, longitude coordinates. We have to have both of those parts to define a datum. Those are the key starting points or locations that identify where things are. They're all measured with reference to a datum surface and a set of datum points. Now, we have to know about this because U.S. datums have improved and evolved over time, especially in the past 3 decades with new technology. And so we have a succession of datums, and one datum is different than another in that the set of points are different and their locations, even for the same point, change slightly. So if you have the wrong datum, you're going to misalign your data in different layers, or when you join data that's of the same theme together from different collection efforts, they won't line up right, and it'll be a mess. And this happens constantly because people don't realize we have different datums, and you can't treat them all the same. We can convert between these different datums, but we have to be careful when we do it, and if we do it wrong, we'll ruin our data. This happens quite often. That's horizontal locations. Vertical points we measure with reference to something called the geoid. We don't use mean sea level. This geoid is kind of like mean sea level, but it's not really. We used to use mean sea level, but there are issues with that I'll talk about later. And so we use heights relative to this geoid, which is defined by gravity. And these geoid or gravity surface measurements have improved over the last 3 decades. And so we have different height bases. Now, they haven't changed as much as the datums have, the horizontal positions. So there's less error, but there still are errors if you aren't careful about using the right, proper vertical datum, proper geoid. So we think about the world like this every day. It's basically a flat surface because on human dimensions, things do appear flat. And we map onto this planar surface. And on the old days, they would actually use what's called a plane table and map the physical locations of things scaled to a table onto a piece of paper, and then they would convert them. Coordinate geometry came in with theodolites and instruments that allowed people to measure angles and distances and reduce locations to a set of numbers, but still we had this idea of a planar surface. And in this surface, we have a coordinate system where we have northings or y values that run north-south and eastings or east values that run east-west. And the coordinates are always parallel. Now, typically, these lines approximately head north-south. One of the lines heads north-south and the others don't. But they're parallel in our grid system. So we have this Cartesian system where the lines are parallel and never intersect, the lines in one direction. So the y lines don't intersect and the x lines or east lines never intersect. The problem is we can't use this over large areas without incurring some distortion, because when you try and lay this flat surface on the curved Earth, the Earth curves away from this flat surface. The bigger the area we map with a flat surface, the bigger the curvature and the separation, and that sticks or creates distortion in distance and area and angles. From southern to northern Minnesota, if you tried to use one flat surface for the whole state, you would get tens of feet of error in measurement, so you'd mislocate things. And depending upon where you started and how you did your measurements, things wouldn't line up correctly. So we have to somehow render the curved surface onto a flat surface, and that's the second part. In the next lecture, you would do that in map projections. But because of this curvature and our need to work in a curved surface to measure things carefully, we have to know about spherical coordinates and measurements in spherical coordinates, because all measurements are done on the curved surface of the Earth, assuming a curved Earth, and then converted into a flat or planar map surface. Definitionally here, a longitude is a measurement of an angle spun from an origin. And so they're 360 degrees all the way around the globe at the equator, or actually at any point here. And there are 360 degrees around the poles. The longitudes, we typically start at a point that's off the coast of Africa and measure east and west from there for 180 degrees. So we have a positive and a minus 180 degrees, as we talked about in the last week's readings. But they'll go from 0 to 180 and 0 to minus 180 for 360 total. Latitudes go from 0 to 90, and on the opposite side, 0 to 90 from south to north, from the equator to north. From the equator to south, they go from 0 to minus 90, so there's 180 here and 180 there, so it's a spherical system. That plus a radius in a sphere will locate yourself anywhere in three-dimensional space. And if we have an ellipsoid which has a slightly different form, we have two radii as described in the book. Now I won't show an example of it here because we don't get into the calculations much, but ellipsoid really is a better measure of the shape of the Earth as it's spinning, as Isaac Newton first deduced. It squishes the Earth and pulls it out at the center, the centrifugal force, and so we have two radii. The equations are a little bit more difficult in calculation, but the notions are all the same. We have a latitude and a longitude and a distance out from the center, right? So why are there 360 degrees in a circle? Why do we use this weird number, and why are there 60 minutes in a second and 60 seconds in a and 60 minutes in a degree and 60 seconds in a minute? Well, thank the Sumerians from 4,000 years ago. They realized that if I had a set of triangles, right, with equal sides, these are equilateral triangles, if I laid 6 of them around together, I would get basically a definition where the outer points can define a circle. So if I were to take a string with a point of that radius and drag it around, I could fit 6 of these triangles inside here, so it's 1/6. And they would use that to their advantage in building or in calculations from geometry, because you could take a stick and mark it into 100 different pieces of equal width, and then you could have basically measure along here in hundredths or in 60ths. And so what they found is, look, we had 360 degrees around here because they want to divide this into sort of 60-degree segments. And so they basically had a 6 by 10 base system, and they decided, well, we're going to split this by 60 and then the next one by 60 and the next one by 60 to use calculations. And we've carried that down through time. Latitude longitude is not a Cartesian system, and remember, Cartesian system, the parallel lines never intersect. Well, the lines aren't parallel here for constant longitudes. If I go north crossing the latitudes and constant longitude, I eventually at the North Pole and South Pole are going to intersect all other lines of constant longitude, and so they're going to hit there at the top. They converge. So there's nothing really Cartesian about this because they're not parallel. They intersect. These lines that form our grid, Cartesian, they are at right angles. Now, because we're doing measurements on curved surfaces, a lot of our calculations here involve the radii and turned angles. And distances measured on the surface we calculate often by doing angle measurements and knowing this radius. So we can make a measurement to a star from 2 locations, and that difference in the angle then we can measure, And from that difference in the angle, because we'll measure basically a local vertical here and a local vertical here, we can measure the angle of the stars, and through some trigonometry we can figure out what this angle is. And if we know what the radius is, we can get the distance. So we often use these radius measures along with angle measures to get distances in spherical surveying. But we have to make sure we use radians measures, right? 1 radian is 57.2957 degrees. It's basically 1 radius laid along the arc, and there are about 6 of these going around, 6.2 actually, 6.28 going around the whole circle. So if we have an angle, we have to define that angle typically as a radian measure, not as a degree measure. They don't go from 0 to 360 all the way around, but rather from 0 to 6.28 all the way around. Anyway, if you see calculations and they have funny numbers for the angles, it's probably because they're using radians. Another thing is that these measurements on the surface of the Earth are always in the shortest distance. Just like on a grid, when we say how far is something, it's what's the shortest distance, because everything is an infinite distance from everything else if I don't walk there directly. So the shortest distance is a straight line, and on a sphere, the shortest distance are these great circles. Great circles are lines on a circle that lies on a plane that cuts through the center. So you basically have a plane, it goes through the Earth, but it has to hit that center of the Earth from where the radius comes, and then any line on that intersection between the globe and the plane is a great circle arc, and the great circle arcs at a shorter distance. Now, these great circle arcs often look funny when you don't look at them from directly above because they look curved, but they're not curved. And that's why when we're flying any place that's not on line of equal latitude or equal longitude at the equator, we fly what appear to be curved. We cross a bunch of latitudes and longitudes. You wouldn't, looking at a normal map, think this was the best way to get from New York to Delhi, but flying over the North Pole actually is. On most maps you'd think, oh, I want to cut across Europe. But that's because the maps are distorted. They're not 3D globes. We can't see the great circle arcs on most maps. There are also small circles. Those are circles for planes that cut the globe but don't go through the center. And our lines of equal latitude are all small circles. So often the shortest way to get to some place is not to, if it's due east of you, is not to head due east, but rather head in a different northerly direction and then eventually in a southerly direction, because that's the great circle route, and that'll be shorter than following due east or due west. If we're walking, it's usually we're not walking that far. If we're flying, we often do follow in these great circle arcs because we're going a long distance, right? As I said earlier, horizontal datums are a reference sphere and a set of well-measured points where I'm using the word sphere to include ellipsoids, these flattened spheres, because they're a special class of sphere. They're a sphere with basically an A and a B, semi-major and semi-minor axis. You actually probably might be better off thinking of a sphere as a special class of ellipsoid where the A and the B are equal. And the Earth is flattened so that we do have an A and a B. And the best geometric shape that fits the approximate shape of the Earth, or the actual shape of the Earth that approximates the actual shape of the Earth, is an ellipsoid. The Earth is flattened some. Now, it doesn't fit it perfectly. The Earth undulates above and below, and it undulates above and below it in various ways, which we'll talk about when we talk about the geoid. But on top of that, then we'll do these measurements along great circle distances between known points. We'll do multiple measurements and precisely calculate where the locations are, because we can come at them from all sorts of different directions. So we'll benchmark these points historically. Now we use GPS stations that are permanent at some of these points, but nonetheless we calculate their locations very accurately, and these points plus a specified ellipsoid with a given A and B and a given origin for the ellipsoid define a datum. Well, how do we know where anything is? Right? How do we know where the origin should be, or what measurements are? What's the shape? It all comes down to measuring the stars from the Earth and measuring time very precisely. So the Earth at any given day, at any given time of that day, is in the exact same location. Now, it takes another year for it to come around and spin and be in that exact same location. But the stars are so far away that if I make a measurement on one day to a set of stars at a given time, and another day, at that same time, the next day, the shift is imperceptible because the stars are so far away. So I can make measurements to stars, and if I pay attention to the time at which I'm taking those measurements, I can fix a point on the surface of the Earth. And if I do that from multiple points, measurements to stars, I can establish the relative locations of points on the surface of the Earth by measurements to stars. Stars don't move in our lifetime or in the lifetime of the span of civilization. They're in the same location as far as we can see. Now, the most advanced measurement techniques have established that, yeah, the stars are moving relative to each other and relative to us, but they've also established those movements are so tiny that they don't affect our ability to locate points on the surface of the Earth. So we're basically measuring celestial bodies. Used to be the stars and the moon, but now we've switched to quasars, which are pretty far away. So in the old days, we used to make these measurements on the surface of the Earth to stars using precise telescopes, and we would measure a bunch of points and measure between those points and calculate then the latitudes and longitudes of those points and all the points that we measure on the ground between them. So we had some points that were really precisely measured with astronomical observations over years at different nights under different conditions at different positions, different times of the year, and locate those points relative positions really carefully and establish a key set of latitudes and longitudes. Then we'd ground survey in between those points to connect them. Well, the problem is that all coordinates are measured, right? So we're measuring intensity to the stars from a point, and then we're surveying between them by using theodolites and optical instruments and pulling chain, or later on electronic distance meters, lasers, those sorts of things. But they all contain some kind of error. I didn't exactly line this up over the last point. There was some optical interference and refraction, so that changed the optics slightly. I wrote something down wrong. It was a cold or a warm day, and so the cable that we used to measure distance expanded or contracted. And taken together, these errors get quite large over large networks. We have to basically pull those errors out. Well, along about the 1980s, people realized if we use satellites and we're very careful about measuring from the satellites, and then if we measure signals from very distant quasars, basically pulsing stars that send radio waves, we can combine to get global precise measurements at unheard of before accuracies, millimeter accuracies, hundredth of inch accuracies across the globe. And so between the 1980s and today, basically at the 2010s, they developed that technology, and that's when all our datums started to shift. So right now we use this combination of systems where we use this thing called very long baseline interferometry, big antennas, 100 or so of them around the world, sit on different continents, measuring from quasars. These are pulsing stars way the heck off. And if you correlate the signals and back calculate, you can say at every instant in time where each one of these antennas were. So we can get the main continental positions from those to millimeter accuracy, to accuracies that are the width of a hair. Lots of measurements, long calculations, but the physicists figured this out and have tested it, and it's just amazing that we can do that. And if we combine that with satellites flying around the Earth plus other measurements, so laser measurements from the ground to satellites that are flying around the Earth, and intensive measurements of those satellites, or Doppler effects for changes in the movement, GPS satellites, we can specify the positions for lots more points. So we use the VLBI to locate GPS communication stations, and then those GPS communication stations can use the GPS satellites to locate other points very precisely. And this is how we get these inch level or sub-inch level measurements in positions. This is how we can measure the speed of tectonic plate movement. In the 1960s, people figured out, oh, the plates are moving all around, and that had great ramifications. See, prior to the 1960s, we didn't think the Earth was moving around. We thought, well, surveyors have to go out and carefully measure everything, but everything is static. Once I'm done measuring a continent, I'm done. Well, maybe not in the vertical because things will erode or earthquakes will push things up or down, but horizontally, the distance from Rome to Washington, D.C. was going to be the same forever. We just thought the Earth was static and erosion maybe eroded away the surface, but we didn't really think that plates moved around. But by the mid-1960s, enough data accrued that said, nah, these plates are moving. And that changed how geodesists thought about how we had to measure things. And really, it complicates our lives because it's really the latitude-longitude grid with these continents moving under it. So we had to come up with a system to fix that latitude-longitude grid that was independent of measurements on the surface and then measure to the stars. And so that's where this VLBI idea came along. And then using the GPS to measure a denser set of points. So here's basically the various plates, and along the edges here active volcanoes, because where a plate goes down or comes up, it fractures the surface and lava comes up more easily. And these arrows show the direction and the relative speed of movement, right? The Pacific plate is moving like heck towards Japan. The North American plate is kind of moving in a west-southwesterly direction. The African plate is moving east. The South American plate is moving north, but relatively slowly, while the Nazca plate moves to the east very rapidly. So anyway, these plates are moving around. But with this system, we can now measure in real time the velocity of continents, how much things are moving, both as they move slowly day in and day out, and then when there are earthquakes and things shift a bunch along a plate line. So we're switching from having these rapidly updated datums, we just finally have given in, and the next datum update is just going to be a time-dependent datum. We have to measure the epoch, or the time at which we collect any data, and enter that in with the data so that we can adjust to data collected over different time periods at these high accuracies to match. So we have a whole bunch of datums that we've calculated as the equipment got better between 1980 and now. We try not to let that confuse us while we're putting our data together. Okay. I said that the vertical is measured differently from the horizontal. It's because the Earth is lumpy. The Earth has varying density, and so it pulls the Earth in more in some places than others. So here off the Indian Ocean, there's dense stuff below the mantle or down to the core, and that depresses the Earth by about 100 meters, 300 feet. Up here near Iceland, it's a lighter material, and so the Earth is 230 feet or 40 feet higher than sort of the mean of the Earth. So we have this thing called a geoid, which is different from an ellipsoid. That is the actual shape of what we would call some average surface of the Earth, right? Some locally average surface of the Earth. It sort of bends up and down because of differences in the pull of gravity. So because we have these various horizontal and vertical systems, and because the Earth is dynamic, we've switched from this system of a static survey network to a dynamic survey network. We use GPS stations placed around the world and reference those GPS stations. So the VLBI fixes where those GPS stations are, and then the GPS stations send out signals that we use to locate ourselves in further surveying. So we kind of threw away this survey network. We don't use it really anymore. And the problem is that we had this survey network we built and densified from 1930 to 1980, and we're in the process of calculating the positions for these static locations when GPS became available. And so right around mid-1980, we had several competing versions of datums, those associated with the old survey networks on using optical methods and those GPS-based ones. And then between the late 80s to 2010, we refined the GPS technology and went to basically satellite-derived datums and systems, and that's what we're going to use going forward. But we were also developing GIS and GIS data in a big way in that same period, so there's kind of this confusing mess of various datums being used and being talked about, right? We have to be careful to realize that we have a measured location somewhere on the physical surface of the Earth, here on the ground. We reduce always these coordinates down to the ellipsoid, onto that imaginary curved surface, mathematically curved surface. So every point on a line normal to that ellipsoid is at the same latitude and longitude. So if I come up at a right angle from the ellipsoid, I get a location, and that's the same latitude as everything along this line, down into the Earth or above the Earth. Right, so we have a mass center 0, 0, and an ellipsoid, and I go to a right angle to it. That's where we're defining everything. Right? Heights we measure relative to this point here, this point on the surface. This is our reference surface, right? So remember, that's the way we define a datum, is the reference surface, then well-defined points on them. So any location here, we're measuring relative to some other location that's in our well-defined set. Okay, it's GPS towers now. It used to be those benchmarks from physical surveys before. So we had this split where the datums were national because it was hard, or continental. It was hard to survey across the oceans. We had an origin at the geometric center of the Earth, not the mass center, because we couldn't calculate the mass center of the Earth. We could only calculate the geometric center from measurements on the surface of the globe. We didn't know where the mass center was. It wasn't until we got satellites we could really calculate the mass center, because the mass center really affects the trajectory of the satellites around the globe. We fixed a station of measurements and propagated air from there and assumed a static network of points, that is, the Earth wasn't moving. But between plate tectonics and the improvement in technology, we decided, well, global datums are better because we can use measurements from all over the globe, and they can be recalculated often because we have new computers. Well, with the origin at the mass center, not the geometric center, because satellites allow us to measure the mass center, and we can distribute the error across the whole network equitably, rather than saying some points we're going to fix, we're going to measure out from them. And because we have this GPS which measures every day, we can incorporate and measure point velocities, right? So you have this big pre- and post-satellite datum shift, where post-satellite datums are much better, much more accurate, and pre are as good as they could be given the technology. And there's an evolution in between from mid-1980s to 2011 of the accuracies we could obtain with the old methods to the better accuracies we can obtain with satellite methods. Right? Why do these positions change? Well, two things change. In an early measurement, like this ellipsoid A, I might only have a few points, and I only show 2, 0.5 and 0.1 measured, and I can fit the surface to that. Later on, I measure a whole bunch more at a high level accuracy, right? So these points are on the surface. The one's 0.4, 6, 1, 7. A different ellipsoid is going to fit. So I'll have different origins, different locations. Okay, so that's what's happened really in the world today. We have an ellipsoid that we use in North America, the NAD83 ellipsoid, based on this thing called the GRS80. And then we have the WGS84/ITRF, an ellipsoid that the rest of the world uses, because the rest of the world adopted their standard after satellite datums were put in place, satellite measurements. Ours was established before, and rather than switch to the new one and cause confusion, because people had measured locations relative to our NAD83 for a bunch of years, we said, well, we're just going to use the old one, and then when we want to bring in data from the ITRF WGS84, we'll calculate the mathematical formulas that allow us to do that without injecting any error. So there's an offset of about 2 meters, a little 2.2 meters between the mass center and the geometric center origin. But we just went ahead and used our old one in the US to not confuse and really make a lot of mistakes for the surveying. Right? So that means that if we go down to two different surfaces from the same point of the surface of the Earth, so if we go down to two different ellipsoids, our NAD83 and our ITRF or WGS84, because of this shift, these are going to fall at different latitudes and longitudes. If I pull data in, I collected an ITRF and use it with the NAD83, it's going to be in the wrong location, right? Unless I do some sort of transformation. And that's the main mistake a lot of people make. GPS is collected in this ITRF WGS84 coordinate system. We do most of our data analysis, our data storage, our calculations in an N8083 system, a different datum. And if we don't do that datum switch, we end up with errors in our data, a meter or so, 3 feet, quite commonly. So that means the closest you can get something, if you don't do this right, is within a couple of feet of accuracy. That's also why when you look at data, you often have different coordinate systems for the same point. So here's a benchmark point with the coordinates in N8083, and these are different datums, means they're different coordinate systems. So this is 44 degrees, 57 minutes, 23.23 seconds. 44 degrees, 57 minutes, 23.22 seconds. And you might not think that's a big difference, but some of these are off by tens of feet. Right? So here's a different 44, 57, 23.23. Now the key here is that these latitudes and longitudes are different, but they're different in a consistent way. So this is the 1996 datum. This is the 2007 datum. Here's the original 1986 datum. So this 1986 datum is a spheroid, an ellipsoid, and a set of points in their best location that we can determine. By 96, we calculated that this point is in a slightly different location. So we recalculated its position. Now, it's not in a different location because it moved. It's in a different location because the measurements got better. Remember, we're still using our old pre-satellite base for this calculation. And in 2007, the same thing. We basically have calculated another slight shift, but way out here from 047 to 074. So this shift is small compared to this shift from 86 to 96, then 96 to 2007, which means that we've refined the data and we've gotten the measurements as good as we can. But suffice to say, there are different versions of the coordinates for the same point because they use different datums and improving datum. How much can these shifts be? Well, they tend to be biggest between different families of datums. So I have the N8027, which is kind of a really old static datum, a North American datum in 1927. When I shift to the N8083 here in North America, I get 30, 40 meters, so 100, up to actually 200 feet of shift in the same points. It has nothing to do with tectonic drift, it's just that our measurements got that much better. And then when we went from 83 in 86, which is based on surveys, optical surveys, to 83 in 88 or 9, which is based on GPS, the Harn network, they moved a couple inches. And then CORS 96, better GPS surveying, they moved a couple more inches. Then in 2007 and 2011, they're moving sub-inches. So we basically had this improvement, but now using our old model of the shape and center of the Earth with our old ellipsoid, we're really not improving any things. And so the 2011, there was another set. It improved mostly in the west and southwest. According to most of the country, it didn't improve much. So we're kind of done with this N8083 series. We've measured it as well as we can using satellites. But again, there's this different family, the WGS84, that's optimized to fit for the whole globe rather than just for North America. And that's about a meter off. So if I locate something in my GPS using this WGS84 and I pooch or mess up the conversion to the N8083 1996 or 2007 or one of these others, my data won't align by a meter. Now, in some analysis, you don't care. If you're looking at, I don't know, harvesting huge areas or crop acreage, a few meters one way or another doesn't make a difference. But if you're building a road or trying to relocate a plot, a meter will make a huge difference. And so this WGS84, which GPS collects in, is in a different datum. It's not going to fall. This point should be down here on one of these if I use the correct datum. And so I have to calculate the difference between them, right? So our coordinates change with each different family of datums, from N8083 to ITRF. And our coordinates change with each update of a datum. If I get a new ITRF, it's going to change because I've measured more points better. And the ITRF is a global datum. It also takes into continental drift. So as the continents have drifted, the coordinates will change. In N8083, the coordinates will change, but mostly because we're assuming kind of a static plate. They'll change because our measurements got better. And once our measurements get good enough, then they don't change. Our datum change through time because in each family we've gotten more and better measurements, and so more and better datums. But the differences between families are going to remain until they somehow get aligned. So you have those two things to worry about. Old to new changes within a family, and then the difference between families of datums. Now I put together this in the second or third draft of the book to try and make this clear. So we have different families of datums, and we have updates for those datums. Now this is really kind of the same family. I just put it in for completeness because the WS84 was aligned with the ITRF starting in basically the 1990s. And so the coordinates hardly differ. You know, a couple of centimeters, an inch, a half an inch, something like that. Function, they're equivalent for most work that's non-geodesist work, most GIS work. The NAD83 to these families varies by 2 meters. 1 meter to 2 meters is pretty common. So it doesn't matter how much better we get measurement because the difference in the assumptions of the shape of that ellipsoid, that part, they're just going to be off. Improvements in the measurements as we go down the NAD83 family causes shifts in the coordinates like I showed in that graph before. So the original NAD83 1986 from optical methods to the first GPS-based one, the NAD83 Harn, I had a shift of about 1 meter, 3 feet. Now, they on average, some were bigger, some were smaller, but the average is something like 3 feet. The Harn then to the next CORS 96, so Harn basically as each state got to do their own because the GPS came out and they couldn't coordinate it well enough. And they said, well, we'll coordinate it with time. And that's what the CORS 96 is. Each state came out with their own, and they said, well, then we're going to take all this data federally and analyze it together and remove the errors and fix it as best we can, and then come out with a set of points. And so we got another 2 to 10 inches of shift between the Harn and the CORS 96. And then we did a bunch more measurements and tried to improve it, but those only improve the measurements by about 1 inch, important for geodesists, but not for everybody else. And then from the 2007 to 2011, it's like half an inch or less. So these are various versions. The one you have to be the most careful about is this NAD83 1986 versus NAD83 CORS 96 2007 2011. These are kind of the same. These are different because the shift of a meter is important for a lot of people. Now we have the WGS84, which has changed through time, and the ITRF, different versions. We can basically convert from these using something called a datum transformation, but we have to be careful and make sure we do it correctly. Typically when you come out with a new datum, like the ITRF 94, they give you a way mathematically to calculate the coordinates in the previous datum, so you don't lose all the data, all the coordinates you've collected before. Well, they allow you to collect data and combine it with past data, or to convert the past data to the coordinates we're using in the new datum. Right? So these shifts basically we can account for. It shifted everything to the north and east by 3 centimeters. Well, okay, new measurements now are going to be shifted relative to old ones that way, but if we put the old one in the new datum, then they'll line up. So we do these datum transformations each time we come up with a datum, and typically they'll calculate the datum transformation to the most recent datum in the family and to the current datum in the other families. So when it came with the ITRF 94, they calculated the datum transformation to this WS84 G863 and to the CORS 96. Right? So these calculated conversions back and forth. That way, if I have something in the ITRF 2008, I can go backwards to find out where these things were in the 94 and across to compare them to the NAD83. There are tools that have been set up. This NOAA tool, a National Geodetic Survey in NOAA, has basically an interactive horizontal conversion tool. It's the horizontal time-dependent positioning. And it's time-dependent because it incorporates how things are moving. And so if I measure something and want to combine it with data measured at a different time, I have to say, well, how much did the North American plate move that I'm adjusting for to get my NAD83s? So you go on the website, you type in your coordinates, and it tells you where they were at any given time or are going to be. If you're not in the right datum, you can be off by a few inches to tens of feet, well, 6 feet, unless you're going way back to the NAD 27, which we hardly see anymore. So we use this transformation to make sure we're going to be able to switch datum. Now, you can do this in a couple of ways. In this class, we're going to be doing it within ArcGIS. They bury the datum transformation inside the map projection process. So sometimes you do a projection, all you're really doing is datum transformation if you go from one geographic system to another. Or we can do it in these NGS programs I talked about, the HTTP and the NADCON. So what is a datum transformation? Well, we have an X and a Y here for our current coordinate system, our current datum, and we want to go to a different datum, an X prime, Y prime. So there's three things we do. First, we calculate any switch in the origin. The X and Y might switch. We have a delta X and a delta Y, and maybe a delta Z. So the coordinate system switches. We might scale, so the distances are measured. Usually scale factors are small or just 1. Then there are rotations in the X, Y, and Z. And we're saying, okay, if we had an old measurement on this point, if we do a certain rotation, scaling, and translation, we get the new point on the new surface. So we can run through this mathematical model to calculate this translation, rotation, and scale. It's just a set of equations. Now you can set these set of equations inside the tool. The thing you have to be careful about is to make sure you get the input and output ones right. I'm going from NAD 83 2011 to the WGS 84, so I collected some GPS data, and I'm going to convert that GPS data to my NAD 83 for use here in North America and shift it the meter or 80 centimeters or however far it is. Those things need to shift, right? You run into this all the time when you have various data you've collected and want to combine them. This really helps you define and describe your data collection process because you know the accuracy of the data collection. How accurate does it have to be to make sure that we maintain that accuracy across datum transformations? Because frankly, a lot of data people are collecting in very coarse resolution and they don't really care. If you're, again, measuring stand boundaries or the area of a lake, for the most part, you might accept a GPS that are off by 3 meters, 10 feet. Well, the datum transformations in modern datums are always less than that. But the most valuable data, the most expensive data to collect are the really high resolution, high quality data, the inch level data, although GPS is making that pretty inexpensive to collect. And once we get inch level data everywhere, we're not going to want to degrade that data using a bad transformation. So we can look at this and decide how big an error a specific datum transformation is going to cause, right? And we can go from any data to any other data here by going up or down the chain. If I have data in ITRF 08 and I want to combine it with ITRF 94, I can say, well, I can do this datum transformation, then this datum transformation, then this datum transformation, because they did typically just back to the most recent one. If I want to get the NSRS 2007 version data, I can do this datum transformation, then across to the 94, and then down. So typically, like I said, they do the current one in the other family at the time, and the previous one in the current family, and that allows you to be able to traverse this set of datums to get your coordinates into the same language, right? Inside of ARC, you see that. So inside the project command, I have an output coordinate system, and it'll put in what it calls a geographic transformation. It's a datum transformation. It says I'm using the equation to go from the NAD 83 Cores 96 to the NAD 83 2011. It's doing that datum transformation along here, Cores 96 down to 2011. Now, sometimes when you have to go up multiple and across, you'll see these plus signs because it's saying, oh, I need to do 2, right? From the NAD 83 to the Harn, Minnesota, and then from the Harn to the Cores 96, right? So it's going from NAD 83 to the Cores 96, but it has to do this Harn one in between. It's basically saying, oh, I want to go from here to here, so I'll do this transformation, then this transformation to get back. So that's why it sometimes gives you these weird ones. It'll give you various choices. Okay. You have to be careful in ARC because there are two big differences. If we look back here, right, the pre-1989 data and then the post. So this is satellite data and this is pre-satellite data. There's a meter difference, then another 20 centimeters difference, and then this settles down. So these are kind of the same. These are different. These are really different. So I have to be careful to make sure that I pick the right version. If all my data are in this and I collect my new data in this, I want to project over to these. So I want to go from the WGS84 ITRF that GPS collects currently to the CORS 2011. I want to make sure I get this right datum transformation. Well, the problem is the ARC software was written in the 1980s, and they set up this file structure, and so they have this NAD83, which is the 86 version, which unhelpfully they don't put here on any of these. Then down in a different folder, they have this CORS 96. So you have to be insistent. You have to realize, oh, they're saying this is just the original 86 version. And these are the satellite-based ones in this different folder. Because often when you're searching down, you'll say, oh, I see NAD83. That's the one I want. And you go select that. You might look around inside and say, which version is this? And if you pick this when you want to pick this, the actual CORS 96, you're going to have your data off by a meter or so. They should really put 1986 in here. They don't. So that's one of those hazards or landmines or reasons you take a course like this. If you dig into their documentation, you can find their specification of, they'll tell you, oh, yeah, this is why, here's what we mean. But most people don't. Most people just run down the list and find something that looks kind of familiar and goes from there. Okay, we'll talk about heights later.